Hello there, and welcome to the Sleepy Curiosities. I'm so glad you're here. Maybe it's been a long day, or maybe you just like to fall asleep thinking about the quiet details of the universe. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body rest and your thoughts drift, because tonight we're exploring the universe itself. We'll move gently from fact to fact. Some things may surprise you. Others may stay with you like a quiet thought at the edge of sleep. And if these calm explorations help you rest, feel free to like and subscribe. It helps others find their way here too. Now, if you're ready, let's begin. When we ask how large the universe is, the answer is far stranger than a simple number. The observable universe, the part we can actually see and measure, is a sphere with a diameter of about 93 billion light years. This often confuses people because the universe is only about 13.8 billion years old, and nothing travels faster than light. You might expect the radius to be 13.8 billion light years, but space itself has been playing a trick on us. While the light from distant galaxies was traveling toward Earth, the space between us and them was stretching out, expanding like the surface of a balloon being inflated. Light that left a star billions of years ago has had to traverse a path that kept getting longer and longer as it traveled. The galaxy that emitted that light has moved incredibly far away by now, carried by the flow of expansion. So when astronomers calculate where those most distant objects are today, they find they are over 46 billion light years away in every direction. This creates a sphere of reality that we call observable, centered on you right now. Everything outside of this sphere is currently invisible to us, its light having not yet had enough time since the beginning of time to reach our eyes. We are floating in a bubble of light that grows slightly larger with every passing second, revealing just a little more of the dark. This limit to our vision creates something astronomers call the cosmic horizon, which is quite literally the edge of our visible reality. Just like a ship at sea can only see as far as the curvature of the earth allows, we can only see as far as light has been able to travel since the Big Bang. But unlike a horizon on Earth, which moves with you as you walk, the cosmic horizon represents a barrier of time as much as space. When we look toward this horizon, we are looking back in time, seeing the universe as it was billions of years ago. The strange part is that because the universe is expanding, and that expansion is accelerating, distant galaxies are currently being pushed away from us faster than the speed of light. This doesn't break the laws of physics because it is the space itself expanding, not the objects moving through it. But it means that objects near the edge of our vision are slowly passing beyond a point of no return. Once they cross that threshold, their light will never reach us again. They will effectively disappear from our future, severed from our causal reality forever. It is a quiet, continuous process where the universe beyond our reach gets larger, while the number of things we can technically interact with slowly diminishes. A vast, silent door closing very slowly at the edge of the world. Inside this observable sphere, the sheer inventory of what exists has been revised upward in staggering ways. For a long time, astronomers believed there were perhaps a few billion galaxies, which is already a number difficult to comprehend. But recent studies, particularly those using long exposure images from the Hubble Space Telescope, have suggested the number is closer to 2 trillion galaxies. To arrive at this number, astronomers pointed the telescope at a tiny, dark patch of sky, roughly the size of a grain of sand held at arm's length, and left the shutter open for days. In that tiny speck of nothingness, they revealed thousands of distinct galaxies stretching back through time. By extrapolating that density to the entire sky, we reach the 2 trillion figure. Each of these galaxies is a massive island universe of its own, containing anywhere from a few 100 million to 100 trillion stars. If you were to count one galaxy every second, without sleeping or stopping, it would take you over 60,000 years just to count them all. And remember, that is only counting the galaxies, not the stars within them. Most of these are smaller dwarf galaxies, faint and dim, drifting in the silence. It suggests that for every grain of sand on every beach on Earth, there are thousands of solar systems turning in the dark. A crowded infinity that we can mostly only imagine. In contrast to these crowded clusters, there are places in the universe where almost nothing exists at all. One of the most famous of these empty spaces is the Boötes void, often called the Great Nothing. This is a nearly spherical region of space, roughly 330 million light years in diameter. In a typical region of space of this size, we would expect to find thousands of galaxies teeming with stars and life. But in the Boötes void, astronomers have discovered fewer than 60 galaxies in total. It is an expanse of absolute desolation, a desert in the cosmic landscape. The void is so large that if the Milky Way were situated in its center, we wouldn't have known other galaxies existed until the invention of powerful telescopes in the 1960s. For most of human history, looking up at the night sky from such a place would have revealed only our own stars, and then, beyond them, a perfect, unbroken blackness. The void likely formed from the merging of smaller voids over billions of years, like soap bubbles coalescing into larger pockets of air. These voids aren't truly empty. They still contain dark matter and some stray hydrogen atoms, but the density is so low that calling them nothing feels appropriate. Scientists estimate there are many such voids throughout the universe, carved out by the expansion of space and the gravitational pull of matter toward dense regions. It is a quiet reminder that the universe is not evenly spread like butter, but clotted and webbed, leaving vast caverns of silence between the walls of light. A lonely silence in a crowded room. Zooming back into where we live, we recently learned that our galaxy is part of a much larger structure called the Laniakea supercluster. The name is Hawaiian for immeasurable heaven, a fitting title for a structure of such grace and magnitude. Before this discovery in 2014, we knew galaxies grouped together, but we weren't sure where the boundaries lay. Scientists mapped the position and movement of over 8,000 galaxies to determine that we are part of this massive, flowing river of stars. Laniakea spans about 520 million light years and contains the mass of 100 million billion suns, encompassing some 100,000 galaxies. What makes Laniakea defined as a single structure is the way gravity influences the movement within it. It acts like a watershed on a continent. Just as all raindrops falling on one side of a mountain range will eventually flow into the same ocean, all the galaxies within Laniakea are slowly flowing toward a common center of gravity. We are drifting along these invisible gravitational currents, moving in concert with thousands of other galaxies. We are not just isolated in space. We are part of a massive, coherent architecture, a glowing web of light stretched across the dark. It gives us a cosmic address that is far grander than we ever knew. We are residents of a flowing stream of crystal and light, heading toward a destination we will never reach. The destination of this flow is perhaps one of the most intriguing mysteries in our local universe, known as the Great Attractor. All the galaxies in our supercluster, including the Milky Way and Andromeda, are being pulled toward a specific region of space about 150 to 250 million light years away. We are moving toward it at a speed of about 600 kilometers per second. The mystery lies in the fact that we can't easily see what is doing the pulling. The Great Attractor lies in a direction of the sky called the zone of avoidance, which is obscured by the dense dust and stars of our own Milky Way galaxy. It's like trying to see a distant mountain while standing in a thick forest. The trees in front of you block the view. Using radio astronomy and infrared light, which can pass through the dust, scientists have determined there is a massive concentration of mass there, likely a cluster of thousands of galaxies known as the Norma cluster, and perhaps even larger structures beyond that, like the Shapley supercluster. The gravitational force is so immense that it dictates the movement of millions of light years of space. We are being reeled in by a heavy, invisible hand hidden behind the curtain of our own stars. It is a reminder that gravity is the true sculptor of the cosmos, working silently across distances that defy comprehension. A force we cannot see, pulling us toward a place we may never reach. When we ask how old the universe is, we are really asking how long light has been traveling to reach us. The current best estimate places the age of the cosmos at approximately 13.8 billion years. This number is not a guess, but a precise calculation derived from measuring the expansion rate of space itself and running the cosmic film in backward motion. To arrive at this figure, astronomers use the Planck space mission data to measure the oldest light we can see, tracing the expansion back to a singular moment of infinite density. It is difficult to intuitively grasp a span of time this vast. If we were to compress the entire history of the universe into a single calendar year, all of recorded human history, every empire, every war, every invention would take place in the final 14 seconds of December 31st. A human lifetime would be a mere blink of an eye, less than a fraction of a second. This 13.8 billion year timeline gives us a boundary, a horizon beyond which we cannot see, simply because light from further away hasn't had enough time to reach us yet. We exist in a bubble of time, looking outward into the past, seeing the universe not as it is now, but as it was when the light departed its source. It is a concept that turns every telescope into a time machine, allowing us to peer back through the eons toward the very beginning. A silent, ancient clock that has been ticking long before there was anyone to hear it. Before we can speak of stars or galaxies, we must look at the very first moment of time, known as the blank epoch. This is the earliest period of time in the history of the universe, occurring from 0 to approximately 10 to the negative 43 seconds. That is a decimal point followed by 42 zeros, and then a 1, a slice of time so infinitesimally thin that the laws of physics, as we know them, simply cease to exist. During this epoch, the universe was incredibly hot and dense, a singularity where the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were likely fused into a single, unified superforce. We cannot effectively describe what happened here because our current understanding of gravity does not work on such a tiny quantum scale. It is a wall in our knowledge, a veil we have yet to pierce. In this moment, the entire cosmos was smaller than a single proton. There was no matter, only pure, roiling energy. Concepts like space and time were not distinct or stable. The geometry of the universe was likely a chaotic foam of fluctuating dimensions. It is a period that represents the ultimate mystery, a chaotic seed containing the potential for everything that would ever exist. It was a state of being that lasted for a heartbeat so short it defies imagination. Yet it set the stage for the grand expansion that followed. A moment of perfect unity before the separation of the world. Immediately following this earliest epoch, the universe underwent something called cosmic inflation. This was not an explosion in the traditional sense, but a sudden, terrifyingly rapid stretching of space itself. In a fraction of a second, far less than the blink of an eye, the universe expanded from something smaller than a proton to something about the size of a grapefruit. While that size sounds small to us, the scale of the expansion was faster than the speed of light. This does not violate physics, because while objects within space cannot travel faster than light, space itself has no such speed limit. This rapid inflation smoothed out the universe, stretching away any wrinkles or curvatures, much like pulling on the edges of a crumpled bedsheet, until it creates a flat, taut surface. This helps explain why the universe looks roughly the same in every direction we look today. Without this sudden growth, parts of the universe would have been too far apart to exchange energy and equalize their temperatures. Inflation took tiny, random quantum fluctuations, microscopic jitters in the energy field, and stretched them out to cosmic scales. These stretched fluctuations would eventually become the seeds for galaxies and clusters of stars. It was a silent, massive breath, inhaling space into existence, pushing the boundaries of the cosmos outward into the nothingness. A sudden unfolding that created the room for us to eventually exist. For thousands of years after the initial expansion, the universe was a hot, opaque fog. This was a time when light could not travel freely because the cosmos was filled with a dense soup of charged particles, protons and electrons, bouncing around frantically in the intense heat. This period ended roughly 380,000 years after the Big Bang in an event known as recombination. As the universe expanded, it finally cooled down enough to about 3,000 degrees Celsius for electrons to slow down and be captured by protons. This was the birth of the first neutral atoms, primarily hydrogen and helium. It was a pivotal moment of transformation. Before this, a photon of light couldn't travel more than a tiny distance before hitting an electron and scattering, much like sunlight getting lost in a thick cloud. But once the electrons were locked into atoms, the fog suddenly cleared. The charged particles were neutralized, and space became transparent. Light was finally free to travel across the universe without obstruction. This moment marked the separation of matter and radiation, a decoupling that allowed the first light to stream outward in all directions. It was effectively the moment the curtains were pulled back, revealing the stage where the cosmic drama would unfold. The universe shifted from a blinding, dense chaos into a vast, clear darkness, ready to be filled with stars. A great clearing of the mist that allowed the universe to see itself. The light released during that moment of clearing is still with us today, known as the cosmic microwave background radiation, or CMB. It is the oldest light in the universe, a faint afterglow of the Big Bang itself. It was discovered quite by accident in the 1960s by two radio astronomers who couldn't get rid of a persistent hum in their antenna, which they initially thought was caused by pigeon droppings. We now know that this signal comes from every direction in the sky with almost perfect uniformity. It is the heat signature of the infant universe, stretched out and cooled down over 13.8 billion years of expansion. When you see static on an old analog television set, about 1% of that static is actually the cosmic microwave background interacting with the antenna. It is a tangible connection to the beginning of time in your living room. While it looks uniform to the naked eye, precise instruments show tiny fluctuations in temperature, differences of less than 100,000th of a degree. These tiny variations are the baby picture of the cosmos, showing us where matter was slightly denser. These denser spots had slightly stronger gravity, which eventually pulled in more matter to form the first stars and galaxies. Without these tiny imperfections in the smooth background, the universe would have remained a uniform gas, and we would not be here. A whisper from the past that fills the silence between the stars. After the brilliance of the initial flash and the release of the background radiation, the universe entered an era astronomers call the cosmic dark ages. This period lasted for hundreds of millions of years. Despite the dramatic name, it wasn't empty, it was simply dark. The universe was filled with neutral hydrogen gas, but there were no stars to light it up, no galaxies to swirl in the void. It was a time of immense quiet and slow, patient construction. Gravity was the only active sculptor during this long night. In the utter blackness, gravity was gently pulling the drifting clouds of hydrogen and helium together. It amplified those tiny irregularities left over from the Big Bang, gathering gas into denser and denser pockets. There was no light to see, no warmth to feel, just the silent, relentless work of mass attracting mass. It is strange to imagine a universe that is full of matter, but completely invisible to the human eye. If you could stand in that epoch, you would see nothing but absolute blackness in every direction, a darkness deeper than any night sky we know today. Yet, in that darkness, the structure of the future was being built. The gas clouds were growing heavier, heating up as they compressed, preparing to ignite. It was a long, pregnant pause in the cosmic symphony, a deep breath taken before the first note was sung. Eventually, the pressure within these collapsing gas clouds became great enough to ignite nuclear fusion, bringing the dark ages to an end with the birth of the first stars. Astronomers call these the population III stars. These were not like the sun or the stars we see in the night sky today. Because they were formed from the primordial mix of the Big Bang, they were made almost entirely of hydrogen and helium, with no heavier elements like carbon, oxygen, or iron. Without these heavy elements to help cool the gas clouds, these first stars had to be massive to form, likely hundreds of times more massive than our sun. They were colossal, luminous giants, burning with a ferocious blue-hot intensity. Because of their immense size, they lived fast and died young, burning through their fuel in just a few million years, whereas a star like our sun lasts for billions. Their short lives were crucial for our existence. In their cores, they fused hydrogen into heavier elements, and when they exploded in titanic supernovae, they scattered these new elements, carbon for life, calcium for bones, iron for blood, across the universe. They were the ancestors of all future celestial bodies, sacrificing themselves to seed the cosmos with the ingredients necessary for planets and life. We have never seen one of these stars directly, as they are long gone, but their legacy flows in our veins. The first lanterns lit in the dark, burning brightly to pave the way for everything else. Stars begin their lives not as fiery spheres of light, but as cold, silent accumulations of gas and dust. Deep within the vast interstellar clouds known as stellar nurseries or molecular clouds, the temperature can drop to hundreds of degrees below zero. These regions are some of the coldest places in the universe, and yet they are the birthplaces of intense heat. Gravity is the patient sculptor here. Over millions of years, a denser pocket within the cloud begins to pull more material toward it. As the gas falls inward, it swirls and compresses, slowly heating up in the darkness. It creates a protostar, a hidden infant star shrouded in a cocoon of dust that blocks visible light. We can only see these forming stars using infrared telescopes that peer through the veil. The most famous example of this is the Orion Nebula, a stellar nursery visible to the naked eye as a fuzzy patch in Orion's sword. Inside that glowing cloud, thousands of new stars are currently forming, collapsing under their own weight until the pressure in their cores becomes great enough to ignite. It is a slow, gentle accumulation that eventually results in a sudden, brilliant ignition, turning a cold pocket of gas into a blazing sun. A quiet gathering of dust that decides, eventually, to shine. Once a star ignites, it enters a long period of stability defined by a constant, violent tug-of-war between two immense forces. This state is called hydrostatic equilibrium, a delicate balance that keeps the star alive for billions of years. On one side, you have the crushing force of gravity, constantly trying to pull the star's mass inward and collapse it into a single point. On the other side, you have the explosive pressure of nuclear fusion in the core, pushing outward with the power of millions of atomic bombs every second. For a star like our Sun, this process involves fusing roughly 600 million tons of hydrogen into helium every single second. It creates an outward pressure that perfectly counteracts the inward pull of gravity. This standoff determines the size, brightness, and lifespan of the star. It is remarkably stable. Our Sun has maintained this balance for about 4.6 billion years and will likely continue for another 5 billion. It's strange to think that the sunlight warming your face is the result of a chaotic, high-stakes battle between crushing weight and explosive energy, held in a perfect, stable deadlock. It is a violent stillness, a roaring engine that maintains the precise shape of a sphere against the darkness of space. As a star ages and burns through its supply of hydrogen, the delicate balance shifts, leading to a dramatic transformation into a red giant. When the hydrogen in the core is depleted, the core begins to contract and heat up even further, while the outer layers of the star do something unexpected. They expand and cool. As the surface expands, it drifts further from the core's heat, turning from a brilliant white or yellow to a deep, glowing red. This expansion is truly massive in scale. When our own Sun reaches this phase, it will swell to such a size that it will likely swallow the orbits of Mercury and Venus, and possibly even Earth. The surface of the star will become tenuous, more like a hot vacuum than the dense surface we see today. Red giants are relatively cool stars, but because they are so physically large, they are incredibly bright. Inside the core, the star begins fusing helium into carbon, buying itself a little more time against gravity. This phase is the star's autumn, a period of change where it grows grand and luminous before the end. It is a reminder that even the steady, yellow suns we rely on are dynamic, changing things, destined to one day fill the sky with a different kind of light. For low to medium mass stars, the end of life does not come with a bang, but with a beautiful, gentle shedding of layers known as a planetary nebula. The name is actually a historical mistake. When 18th century astronomers first saw these round, fuzzy objects through early telescopes, they thought they looked like planets. In reality, they are the final exhalations of a dying star. As the red giant phase ends, the star becomes unstable and begins to pulse, pushing its outer layers of gas out into space. These layers drift away, forming intricate, glowing shells of gas that can span light years. At the center, the hot, exposed core of the star illuminates this gas, causing it to glow in vivid colors: greens from oxygen, reds from nitrogen and hydrogen. The Ring Nebula and the Helix Nebula are stunning examples of this, looking like cosmic eyes staring back at us. This gas is rich in elements created by the star during its life: carbon, nitrogen, and oxygen, which will eventually mix with the interstellar medium to form new stars and planets. It is a peaceful recycling process. The star doesn't just fade away, it gifts its substance back to the universe, creating a temporary, glowing monument to its own existence. After the outer layers have drifted away, all that remains of the star is its small, incredibly hot core, now called a white dwarf. This is the final resting state for the vast majority of stars in the universe, including our Sun. A white dwarf is an object of extreme paradoxes. It packs the mass of a sun into a sphere roughly the size of Earth. The density is mind-boggling. A single teaspoon of white dwarf material would weigh as much as an elephant, about 5 tons on Earth. Without fusion to generate outward pressure, the star is supported only by something called electron degeneracy pressure, a quantum mechanical effect where electrons refuse to be squeezed any closer together. These dead stars start out incredibly hot, shining with a brilliant white-blue light, but they have no way to generate new energy. Over billions and billions of years, they will slowly radiate their stored heat away, dimming and reddening like a cooling coal in a fireplace. Eventually, in a future far distant than the current age of the universe, they will cool completely to become black dwarfs, invisible and cold. But for now, they stand as hot, dense diamonds in the dark, silent sentinels remembering the fires they once held. While most stars fade quietly, the most massive stars in the universe have a far more dramatic destiny: the supernova. When a star with more than 8 times the mass of the Sun runs out of fuel, it doesn't just collapse, it implodes. These stars have enough pressure to fuse heavier and heavier elements, from helium to carbon to neon, oxygen, silicon, and finally, iron. Iron is the star killer. Fusing iron consumes energy rather than creating it. In a fraction of a second, the fusion stops, and gravity instantly wins. The core collapses from the size of Earth to the size of a city in less than a second, moving at 25% the speed of light. The outer layers rush in, hit the ultra-hard core, and bounce off in a titanic explosion that can briefly outshine an entire galaxy of billions of stars. This explosion is the forge of the cosmos. The intense heat and pressure create the heavy elements like gold, silver, and uranium. Almost every heavy atom in your jewelry or electronics was forged in the split-second death of a massive star billions of years ago. It creates a shockwave that travels for millennia, seeding nearby gas clouds with the ingredients for life. A moment of destruction that allows for future creation. If the remnant core after a supernova is between about 1.4 and 3 times the mass of the Sun, it becomes a neutron star, one of the strangest objects in existence. The collapse is so violent that protons and electrons are smashed together to form neutrons, creating a star made almost entirely of nuclear particles. The density here is beyond human comprehension. Imagine taking the entire human population, all 8 billion of us, and squishing us into the volume of a sugar cube. That is the density of a neutron star. The entire star is only about 20 kilometers or 12 miles across, roughly the size of a city like Manhattan. Yet it contains more mass than the Sun, because they retain the angular momentum of the giant star they used to be, but are now so small they spin incredibly fast, sometimes hundreds of times per second. They also have magnetic fields trillions of times stronger than Earth's. The gravity is so intense that the surface is exceptionally smooth. The highest mountain on a neutron star would be mere millimeters tall. If you were to drop an object from just 1 meter above the surface, it would hit the ground in a microsecond at tremendous speed. They are the extreme laboratories of physics, where matter is pushed to the absolute edge of what is possible. Deep in the cosmos, there are objects that behave with such precision they rival our best atomic clocks. These are pulsars, the rapidly spinning remnants of massive stars that have collapsed under their own weight. When a giant star explodes and leaves behind a neutron star, the conservation of angular momentum causes the core to spin incredibly fast, much like a figure skater pulling in their arms. Some of these stellar cores rotate hundreds of times every single second. As they spin, they emit powerful beams of electromagnetic radiation from their magnetic poles. Because the magnetic poles aren't perfectly aligned with the star's rotation, these beams sweep across the universe like the light from a lighthouse. From our perspective on Earth, we only see the light when the beam points directly at us, creating a steady, rhythmic pulse. When they were first discovered in 1967 by Jocelyn Bell Burnell, the signal was so regular, pulsing every 1.3 seconds, that her team playfully labeled it LGM1, standing for Little Green Men, wondering if they had intercepted an alien transmission. We now know these are natural phenomena, but their stability is legendary. Some pulsars keep time so accurately that they are used to test the fundamental theories of gravity, and could one day serve as a cosmic GPS for spacecraft traveling between the stars. A heartbeat made of pure energy, enduring long after the star has died. While pulsars impress us with their speed, another type of neutron star terrifies with its sheer magnetic power, the magnetar. These are rare, exotic remnants that possess the strongest magnetic fields in the known universe. To give you a sense of this invisible strength, the magnetic field of a magnetar is about 1,000 trillion times stronger than the magnetic field protecting the Earth. If a magnetar were to float halfway between the Earth and the Moon, roughly 190,000 kilometers away, its magnetic influence would be strong enough to wipe the information from every credit card on our planet. But closer up, the effects become even more surreal. The field is so intense that it actually warps the shape of atoms. On Earth, atoms are spherical, with electrons clouding around the nucleus in a round shell. Near a magnetar, the magnetic force compresses these atoms into thin, needle-like cylinders. This distortion changes the fundamental chemistry of matter, making familiar molecular bonds impossible. Occasionally, the solid crust of a magnetar cracks under the strain of these twisting magnetic forces, causing a starquake. These quakes release bright flares of high-energy X-rays and gamma rays that can be detected across the galaxy. It is a place where the forces of nature are turned up to their absolute maximum, creating a silent, invisible cage that nothing can escape unscathed. Not all stellar oddities are violent or extreme. Some are defined by what they failed to become. Brown dwarfs occupy the strange, twilight middle ground between the largest gas giant planets and the smallest stars. Astronomers often call them failed stars because they formed from the same clouds of dust and gas that create stars like our sun. But they never gathered quite enough mass to ignite the steady nuclear fusion of hydrogen in their cores. Without that internal fire to push back against gravity, they simply compress and cool, glowing dimly in infrared light. They are much more massive than Jupiter, sometimes up to 80 times heavier, but they are roughly the same physical size, just incredibly dense. Because they are so cool, typically ranging from room temperature to the heat of a fireplace, their atmospheres can support complex weather patterns that would be impossible on a blazing sun. Scientists have detected storms on brown dwarfs that rival the Great Red Spot, swirling with clouds made not of water vapor, but of hot sand and molten iron. Imagine a world where the rain is made of liquid metal, falling through a sky that glows a dull, dark magenta. They are the quiet introverts of the stellar family, drifting through the dark, warm enough to glow, but too cool to shine. We often imagine stars as solitary wanderers, like our own sun, but the majority of stars in the galaxy are actually born in pairs. These are binary star systems, where two suns are locked in a gravitational dance, orbiting a common center of mass. The dynamics of these systems can create fascinating and complex environments. In some cases, the stars are far apart, taking thousands of years to complete a single waltz. In others, they are so close that they touch, sharing their outer atmospheres in a peanut-shaped embrace. When one star in a close binary system is more massive than the other, it evolves faster, swelling into a red giant. If it gets too close to its companion, the smaller star's gravity can begin to strip material away from the giant, sipping its gas like a cosmic straw. This process, known as accretion, can rejuvenate the smaller star, making it burn hotter and appear younger than it truly is, a phenomenon astronomers whimsically call vampire stars. For any planets orbiting in such a system, the sky would be a constant display of shifting light. You might experience a sunrise with a bright yellow star, followed hours later by the rising of a dim red companion, creating double shadows that stretch and rotate across the landscape. It is a reminder that in the universe, gravity ensures that almost nothing truly travels alone. Occasionally, a star is forced to travel alone, kicked out of its home in an event of cosmic violence. These are known as hypervelocity stars, and they move at speeds that defy the normal rotation of the galaxy. Most stars in the Milky Way orbit the center at a calm, predictable pace, but hypervelocity stars have been clocked traveling at over 2 million miles per hour. The story of their exile usually begins in the chaotic center of the galaxy, near the supermassive black hole, Sagittarius A. Astronomers believe these stars were once part of a binary pair that wandered too close to the black hole. As they swung around the gravitational monster, the intense forces disrupted the binary bond. One star was captured or consumed by the black hole, while the other was slung outward with tremendous energy, like a stone from a celestial slingshot. This survivor screams through the galactic disk, moving so fast that the galaxy's gravity can no longer hold it. It will eventually cross the invisible boundary into intergalactic space, leaving the Milky Way forever. These stars are destined to drift in the immense, empty voids between galaxies, shining their light into nothingness, eternal travelers on a one-way journey into the dark. While hypervelocity stars impress us with speed, the star known as Stephenson 218 astounds us with sheer, incomprehensible scale. Currently holding the title for the largest known star, it is a red supergiant located about 20,000 light years away in the constellation Scutum. To understand how big this star is, we have to abandon normal measurements. If you were to replace our Sun with Stephenson 218, its surface would extend out past the orbit of Earth, past Mars, past Jupiter, and all the way to the orbit of Saturn. It is roughly 2,150 times wider than the Sun. If you could fly a commercial airplane along the surface of our Sun, the journey would take about 6 months. If you flew that same airplane around Stephenson 218, the trip would take 1,000 years. The star is so large that its outer layers are incredibly diffuse, less like a solid surface and more like a hot, glowing vacuum. It is shedding mass at a furious rate, breathing out great clouds of dust and gas that will eventually form new star systems. Objects of this size are rare and short-lived, balancing precariously against gravity for only a few million years before they inevitably collapse. It stands as a momentary monument to excess, a giant lantern illuminating the heavy dust clouds of the galaxy's arm. Among the strange residents of the Milky Way, there is one that seems to break the timeline of creation itself. It is officially named HD 140,283, but astronomers call it the Methuselah star, after the longest-lived figure in the Bible. Located just 190 light-years away, it is a fast-moving subgiant that has puzzled scientists for decades. When astronomers first calculated its age based on its brightness and temperature, the results were baffling. The star appeared to be roughly 16 billion years old. The problem, of course, is that the universe itself is determined to be only 13.8 billion years old. A star cannot be older than the cosmos that contains it. This paradox forced scientists to look closer. They found that the star contains almost no iron, which means it must have formed before the universe was filled with heavy metals from supernova explosions, a relic from a very early generation of stars. By refining their measurements and accounting for the complex physics of how oxygen moves in the star's core, they adjusted the estimated age to roughly 14.5 billion years, with a margin of error that just barely allows it to fit within the age of the universe. It is likely one of the oldest objects we can see, a silent witness that has watched the entire history of the Milky Way unfold from the very beginning. An ancient lantern, burning quietly since the dawn of time. The boundary of a black hole is not a physical surface, but rather a point of no return known as the event horizon. It marks the precise distance from the center where the gravitational pull becomes strong enough to overwhelm the speed of light itself. To understand this, imagine standing on Earth and throwing a ball into the sky. If you throw it with enough speed, about 11 kilometers per second, it will escape Earth's gravity and travel into space. This is called escape velocity. As an object becomes denser, that required speed increases. At the event horizon of a black hole, the escape velocity exceeds the cosmic speed limit of 300,000 kilometers per second. Since nothing in the universe can travel faster than light, nothing that crosses this threshold can ever return. To an outside observer, the horizon appears as a perfect, spherical shadow against the backdrop of stars, a silhouette of absolute darkness. Interestingly, if you were to approach a supermassive black hole, you wouldn't crash into a wall or feel a sudden bump as you crossed this line. You would simply glide into a region of space from which your image could never again reach the outside world. It is a one-way door in the fabric of the universe, guarding secrets that are forever locked away from our view. a silent boundary where the known universe simply ends. Gravity near these objects behaves in ways that can stretch matter into long, thin shapes, a process astronomers have whimsically named spaghettification. This happens because gravity's strength depends heavily on distance. If you were falling feet first toward a small, dense black hole, your feet would be significantly closer to the center than your head. The gravitational pull on your feet would be much stronger than the pull on your head, stretching your body vertically while simultaneously compressing it horizontally. It is a similar effect to the tides on Earth, where the moon pulls the oceans, but amplified to an extreme degree. For a smaller black hole, these tidal forces are so intense that they would pull an object apart long before it even reached the event horizon. However, for the largest black holes in the universe, the transition is surprisingly gentle. Because the event horizon is so far from the center, the difference in gravity between your head and feet is negligible at the crossing point. You could float across the threshold of a supermassive black hole without feeling any stretching at all, only discovering too late that you were trapped. It is a strange reminder that in the cosmos, the most powerful forces often work in quiet, invisible gradients, a seamless transition into a journey that has no end. At the center of nearly every large galaxy, including our own, lies a supermassive black hole acting as a gravitational anchor. These giants are mind-boggling in scale, containing the mass of millions or even billions of suns compressed into a relatively small region. For a long time, astronomers wondered which came first, the galaxy or the black hole. Current theories suggest they evolved together, growing in tandem like a forest growing around a great, ancient tree. These central giants influence the formation of stars and the shape of the galaxy itself, regulating the flow of gas and energy. Despite their fearsome reputation, supermassive black holes are not indiscriminate vacuum cleaners that suck up everything in the universe. Their gravity works just like the sun's gravity. If our sun were replaced by a black hole of the exact same mass, Earth would not fall in. We would simply continue to orbit in darkness. Stars in the galactic center dance around these holes in stable, elliptical paths for billions of years, safe as long as they don't venture too close. They are the silent, dark hearts of galaxies, holding the spiral arms together through the sheer weight of their presence. A heavy, unseen hand steadying the great rotation of the stars. Our own galaxy, the Milky Way, orbits around a specific supermassive black hole known as Sagittarius A. Located about 26,000 light years from Earth in the direction of the constellation Sagittarius, this object is roughly 4 million times the mass of our Sun. Yet, for all its mass, it is surprisingly compact, fitting within a space not much larger than the orbit of Mercury. We cannot see it directly because it traps all light, but we know it is there by watching the stars around it. For decades, astronomers have tracked individual stars whipping around an invisible point at incredible speeds, moving as if caught in a fierce whirlwind. One star, known as S2, completes a full orbit every 16 years, providing precise data on the dark object it circles. In 2022, humanity finally saw Sagittarius A when the Event Horizon Telescope released an image of the glowing ring of gas surrounding its shadow. It appears as a blurry, orange donut of light, a quiet giant that is currently relatively dormant compared to other active galactic nuclei. It sits there in the dusty center of our galaxy, occasionally snacking on a gas cloud, but mostly sleeping. A dormant sovereign residing in the quiet center of our spiraling home. One of the most profound effects of black holes is their ability to warp the flow of time itself, a phenomenon known as gravitational time dilation. According to Einstein's theories, gravity is not just a force pulling on matter. It is a curvature of space and time. The stronger the gravity, the slower time moves. Near a black hole, this effect becomes extreme. If you were to watch a clock falling toward the event horizon from a safe distance, you would see the hands of that clock tick slower and slower as it approached the darkness. To you, the falling object would appear to slow down, dim, and eventually freeze just outside the horizon, never appearing to fully cross it, its image lingering like a ghost. However, for the person falling in, time would seem to pass normally. They would look at their watch and see the seconds ticking by as usual. But if they looked back at the universe outside, they might see events rushing forward at a frantic pace, potentially witnessing millions of years of cosmic history pass in mere moments. It is a separation of realities where two observers can experience time completely differently, yet both are correct. A place where the steady rhythm of the universe unravels into a long, eternal pause. Despite their name and their ability to trap light, black holes are not completely black, thanks to a theoretical process called Hawking radiation. Proposed by physicist Stephen Hawking in the 1970s, this idea blends quantum mechanics with gravity. In the vacuum of space, pairs of virtual particles are constantly popping into existence and annihilating each other. Usually, they vanish instantly. But near an event horizon, something curious happens. Occasionally, one particle of a pair falls into the black hole, while its partner escapes into space. The escaping particle becomes real radiation, which we can theoretically detect. The energy for this particle's escape comes from the black hole itself, meaning the hole slowly loses mass over time. This suggests that black holes are not eternal prisons, but are slowly evaporating. The process is incredibly slow. A black hole with the mass of our sun would take far longer than the current age of the universe to disappear. But it implies that in the immensely distant future, long after all stars have burned out, the last black holes will fade away in tiny puffs of energy. It is a poetic concept that even the darkest, most permanent-seeming objects in the cosmos are not truly forever. A slow, quiet exhalation that lasts for eons. When two black holes spiral toward each other and collide, they create ripples in the very fabric of space-time called gravitational waves. These events are among the most energetic in the universe, releasing more power in a fraction of a second than all the stars in the visible universe combined. Yet, because space is so stiff, these ripples are incredibly faint by the time they reach us. As the two black holes circle closer and closer, they spin faster, dragging space around them until they merge into a single, larger object. This violent merger sends out invisible waves that stretch and squeeze the space they pass through. In 2015, humanity detected these waves for the first time using massive laser interferometers. The signal was a tiny chirp, lasting less than a second, caused by a collision that happened over 1 billion years ago. As that wave passed through Earth, it stretched our planet and everything on it by a distance smaller than the width of a proton. It was a message carried not by light, but by gravity itself, confirming that space is not a static stage, but a dynamic, moving ocean. These waves allow us to hear the universe in a way that light never could. A deep, resonant vibration from the dark collisions of giants. When we picture a galaxy, most of us immediately imagine the elegant, spinning pinwheel of a spiral galaxy. This is the classic shape of our own Milky Way, a structure defined by a flat, rotating disk with distinct arms curling out from a glowing central bulge. What makes these arms so fascinating is that they aren't solid structures like the spokes of a wheel, but rather waves of density moving through the galaxy's disk. Think of them like a permanent traffic jam on a circular highway. The cars, which represent the stars, move into the jam, slow down, and then eventually move out again. But the jam itself remains in the same place because gas and dust get compressed in these traffic jams. They become the primary factories for new stars. This is why the arms often appear blue. They are lit up by hot, short-lived, young stars that burn brightly and die before they can drift far from their birthplace. The center, meanwhile, is usually yellowish or red, populated by older stars that have been circling the galactic core for billions of years. These spiral galaxies are quite common in our local neighborhood, beautiful islands of order that maintain their shape through a delicate balance of gravity and rotation. They are the cosmic engines of star formation, constantly churning out new lights to populate the dark, spinning slowly in the silence of deep space like vast, luminous storms. In contrast to the elegant spirals, elliptical galaxies possess a much simpler, more subdued beauty. These are the most common type of galaxy in the broader universe, ranging from small dwarfs to the absolute largest giants in the cosmos. Unlike spirals, they don't have flat disks or spiraling arms instead. They are shaped like stretched spheres, or perhaps rugby balls, glowing with a soft, diffuse light that fades gently toward the edges. What defines an elliptical galaxy is its maturity. They are often described as red and dead by astronomers because they have used up almost all of their interstellar gas and dust. Without these raw ingredients, the era of star birth has largely ended for them. Instead of the brilliant blue sparks of new suns, these galaxies are filled with long-lived, cooler red and yellow stars swarming around the center in random, chaotic orbits like bees around a hive. Many of these massive structures likely formed from the collisions of spiral galaxies eons ago. When two spirals merge, their delicate arms are scrambled, and their gas is often stripped away or used up in a burst of activity, leaving behind this calm, spherical remnant. They are the quiet retirement homes of the universe, stable and ancient, holding the history of billions of years in their steady, amber glow, resting quietly after the tumultuous events that created them. Some galaxies, however, refuse to fit into neat categories of spirals or spheres, and we call these the irregular galaxies. These are the chaotic rebels of the cosmos, lacking a defined center or a symmetrical shape. They often look like shapeless clouds, scattered clumps of starlight, or twisted ribbons of gas. This disarray is usually not how they started, rather, it is a scar from a violent past. Many irregular galaxies were once standard spirals or ellipticals that drifted too close to a larger neighbor. The immense gravitational pull of the larger galaxy tugged at them, warping their structure and pulling them out of shape like taffy. A perfect example of this can be seen in the night sky of the southern hemisphere, the large and small Magellanic Clouds. These are two dwarf irregular galaxies currently orbiting the Milky Way, and our galaxy's gravity is slowly distorting them as they pass. Because they are often rich in gas and dust, churned up by these gravitational interactions, irregular galaxies are often hotbeds of star formation. They sparkle with the energy of new creation, born from the disruption of order. They remind us that the universe is dynamic and constantly changing, where even the destruction of a shape can lead to the birth of something wild, new, and brilliantly alive. One of the most profound facts about our own place in the cosmos is that the Milky Way is not a static island, but is currently falling toward a collision. We are locked in a gravitational embrace with our massive neighbor, the Andromeda Galaxy, which is currently about 2.5 million light years away. Every hour, the distance between us shrinks by roughly 400,000 kilometers. In about 4.5 billion years, our two great spiral galaxies will meet. It sounds like a catastrophe, but collision is perhaps the wrong word. It will be more like a blending of ghosts. The spaces between stars are so incredibly vast that when the galaxies merge, it is statistically unlikely that any two individual stars will actually hit each other. Instead, the galaxies will pass through one another, their gravity pulling them back together in a slow cosmic dance that will last for hundreds of millions of years. Eventually, the distinct spiral shapes of both the Milky Way and Andromeda will be lost, their arms scrambled and merged to form a single, massive elliptical galaxy, often nicknamed Milkomeda. For any life forms on a planet during this era, the night sky would be spectacular, a horizon filled with the bright core of the approaching galaxy, eventually settling into a uniform haze of ancient starlight. It is a destiny written in gravity, a slow motion union of giants, while the collision with Andromeda is a future event. The Milky Way is already growing by consuming smaller neighbors, a process known as galactic cannibalism. This is a standard way that large galaxies grow over cosmic time, by pulling in dwarf galaxies that venture too close. Right now, a small collection of stars known as the Sagittarius dwarf spheroidal galaxy is crashing through the disk of the Milky Way on the opposite side of the galactic center from us. It has likely looped around our galaxy several times over billions of years, and each time it passes through, our gravity strips away more of its stars and gas. This process leaves behind beautiful, invisible trails called tidal streams, ribbons of stars that wrap around the Milky Way like yarn around a ball. We can identify these streams because the stars within them move together in a different direction and speed than the native stars of our galaxy. It's a gentle form of consumption. The smaller galaxy isn't destroyed so much as it is dissolved, its stars becoming new citizens of the Milky Way. This tells us that our galaxy is not a single monolithic object, but a patchwork quilt stitched together from the remnants of dozens of smaller systems it has absorbed over its long life. We are a collection of travelers brought together by the irresistible pull of the deep. In the early universe, certain galactic centers burned with a brightness that defies imagination, objects we call quasars. A quasar is powered by a supermassive black hole at the heart of a young galaxy, actively feeding on huge amounts of gas and dust. As this material spirals inward toward the event horizon, it heats up due to friction and gravitational forces, glowing with an intensity that can outshine the entire galaxy surrounding it by 1,000 times. Some quasars are so luminous that they are the most distant objects we can see, their light having traveled to us for over 12 or 13 billion years. When we look at a quasar, we are looking directly into the deep past, seeing the universe as it was when it was essentially a toddler. They are the lighthouses of the deep cosmos, signaling across the expanding dark. The energy they release is colossal, shooting out jets of particles at nearly the speed of light that can extend for hundreds of thousands of light years. Most galaxies, including the Milky Way, likely went through a quasar phase when they were young and fuel was abundant. Now, our black hole is quiet, starving for fuel, but the quasars we see at the edge of the visible universe remind us of the ferocious energy that shaped the structures we inhabit today. A blinding beacon from a time before the Earth was born. Perhaps the most mysterious structure of a galaxy is the one we cannot see at all, the dark matter halo. When astronomers like Vera Rubin first studied how spiral galaxies rotate, they noticed something impossible. According to the laws of physics, stars at the outer edges of a galaxy should move slower than those near the center, just as distant planets orbit the sun more slower than Mercury. But in galaxy after galaxy, the outer stars were moving just as fast as the inner ones. They were moving so fast, in fact, that the visible gravity of the galaxy shouldn't have been enough to hold them. They should have been flung out into deep space. The only explanation was that the visible galaxy, the glowing disk of stars and gas, was sitting inside a much larger, heavier, and invisible sphere of matter. This dark matter halo extends far beyond the visible edge of the galaxy, containing 5 to 10 times more mass than all the stars and gas combined. It acts as the gravitational glue that holds the rotating galaxy together. We live in a disk of light that is merely a small decoration suspended in a vast, invisible scaffold. Without this unseen presence, the beautiful structures of the universe would simply fly apart. It is a humbling reminder that the part of the universe we can see is only a fraction of what is actually there, holding us in the dark. When we look at the solar system, it is easy to think of it as a collection of equal partners, a family of planets orbiting together. But in terms of sheer substance, our neighborhood is essentially a one-person show. The sun accounts for a staggering 99.8% of the total mass of the entire solar system. That means Mercury, Venus, Earth, Mars, the gas giants, all the moons, every asteroid, and every comet combined make up merely a sliver of the remaining 0.2%. And even of that tiny remainder, Jupiter claims more than 2/3. This immense disparity explains why the sun's gravity is the absolute dictator of our local space. It dominates the movement of objects billions of kilometers away, tethering them in elliptical paths against the centrifugal desire to fly off into the galaxy. This mass isn't static, either deep in its core. The sun consumes about 600 million tons of hydrogen every second, fusing it into helium. In doing so, it converts a small fraction of that matter directly into pure energy, which eventually reaches us as sunlight. It is a burn rate that seems impossible to sustain. Yet the sun is so massive that it has been doing this for 4.5 billion years and is only halfway through its life. It is the heavy, burning anchor that keeps our world from drifting endlessly into the cold dark. The sun does not stop at its visible surface. In a very real way, it breathes out into the space around it, creating an atmosphere that extends far beyond the planets. This breath is called the solar wind, a continuous stream of charged particles, mostly protons and electrons, flowing outward at speeds of hundreds of kilometers per second. This wind creates a vast bubble around the solar system known as the heliosphere. We live inside this bubble, and it acts as a protective shield against the harsher environment of interstellar space. The boundary where the solar wind finally runs out of steam and pushes against the thin gas of the galaxy is called the heliopause. It is the true edge of our solar neighborhood. Only two human-made objects, Voyager 1 and Voyager 2, have ever crossed this threshold and sent data back. They discovered that the edge is turbulent and strange, a place where the familiar particles of our home star clash with the ancient cosmic rays from other exploded stars. Without this invisible barrier, the radiation reaching Earth would be far more intense, potentially stripping away atmospheres or making life much more difficult. We are essentially traveling through the galaxy in a cocoon of solar material, protected by the very star that lights our days. Moving outward from the sun, we encounter Jupiter, a planet so large it almost became a star itself. But beyond its beauty, Jupiter plays a critical, often overlooked role as the guardian of the inner solar system. Its massive gravitational field acts like a cosmic vacuum cleaner or a shield, influencing the movement of comets and asteroids. Because Jupiter is so heavy, more than twice as massive as all other planets combined, it attracts debris that might otherwise careen toward Earth and Mars. In 1994, astronomers watched in awe as the comet Shoemaker-Levy 9 was captured by Jupiter's gravity, torn into pieces, and then slammed into the planet's atmosphere, creating fireballs larger than the Earth. If that comet had struck our world instead, it would have been a catastrophic event for all life. Computer simulations suggest that without a Jupiter-sized planet in that specific orbit, the frequency of asteroid impacts on Earth would be 1,000 times higher. we might not be here at all if not for this gas giant intercepting the heavy traffic of the solar system. It sits in the dark distance, silently catching the stones that are thrown our way. Further out lies Saturn, famous for its spectacular ring system, which appears solid and substantial in photographs. However, the reality of these rings is a delicate illusion of light and ice. Despite spanning a width of nearly 280,000 kilometers, wide enough to fit several Earths side by side, the rings are incredibly thin. In many places, the main rings are only about 10 meters thick. If you were to build a scale model where the rings were as wide as a football field, the disk itself would be thinner than a sheet of tissue paper. This vast, flat structure is made of billions of chunks of water ice, ranging in size from tiny grains of dust to boulders the size of a house. They are likely the remains of a moon that was torn apart by Saturn's gravity, or a comet that strayed too close. These icy fragments orbit in perfect synchronization, guided by small shepherd moons that carve gaps in the dust and keep the edges sharp. When the planet tilts edge-on to Earth every 15 years or so, the rings virtually disappear from view, becoming a razor-thin line that is almost impossible to see through a telescope. It is a reminder of how something can be so vast and yet so fragile, a disk of diamonds spinning in the cold. If we look back toward the inner solar system, we find Venus, a planet that behaves like a rebel among its siblings. Almost every planet in our solar system rotates in the same direction, counterclockwise if you were looking down from the sun's north pole. Venus, however, spins clockwise, a phenomenon known as retrograde rotation. This means that if you could stand on the scorching surface of Venus without melting, you would watch the sun rise in the west and set in the east. The rotation is also incredibly slow. It takes Venus 243 Earth days to spin once on its axis, but only 225 Earth days to orbit the sun. Consequently, a single day on Venus lasts longer than its entire year. Scientists believe this backward spin might be the result of a massive collision billions of years ago, an impact so violent it knocked the planet upside down or stalled its rotation entirely before it started spinning the other way. This slow backward turn contributes to its lack of a magnetic field and its terrifyingly thick atmosphere, creating a pressurized, superheated world that traps heat more efficiently than an oven. It is a planet that turns against the grain of the rest, marching to a rhythm entirely its own. On the neighboring world of Mars, the landscape is dominated by a feature that defies our understanding of geology: Olympus Mons. This is the largest volcano in the solar system, a shield volcano so immense that it makes Mount Everest look like a foothill. Olympus Mons stands about 22 kilometers high, roughly 2.5 times the height of Everest. But its height is only part of the story. Its footprint is the size of the entire country of France, or the state of Arizona. If you were standing on the summit, the volcano is so wide that you wouldn't be able to see the base. The gentle slopes would extend beyond the horizon, hidden by the curvature of the planet itself. The reason it grew so large is that Mars lacks plate tectonics. On Earth, the crust moves over hot spots, creating chains of smaller volcanoes like the Hawaiian Islands. On Mars, the crust stayed still, allowing lava to pile up in the same spot for millions of years. The caldera at the summit, the opening of the volcano, is 80 kilometers wide, large enough to swallow entire cities. It reaches so high that it pierces through most of the Martian atmosphere, standing in the near vacuum of space, a monument to fire on a frozen, silent world. Journeying back to the outer reaches, we find Uranus, the ice giant that rolls through space on its side. While most planets spin like spinning tops with a slight tilt, Earth is tilted about 23 degrees. Uranus is tilted at an extreme 98 degrees. Its axis of rotation is almost parallel to the plane of the solar system. This means that its north and south poles are located where most other planets have their equators. The result is the most extreme seasonal cycle in the solar system. As Uranus takes 84 Earth years to orbit the Sun, each pole gets 42 years of continuous sunlight, followed by 42 years of total darkness. Imagine a summer that lasts for 4 decades, where the sun never sets, circling overhead in the sky, followed by a winter night that lasts just as long. This strange orientation is likely the scar of another ancient cosmic violence, a collision with an Earth-sized object shortly after Uranus formed. The impact knocked the planet over, but it kept its moons and rings, which now orbit perpendicular to the rest of the solar system, like a bull's facing the sun. It drifts along its lonely track, a pale blue eye rolling endlessly through the dark. We often look at the moon as a peaceful, silvery companion that has always been there, watching over the earth in silence. But the leading theory of its origin tells a much more violent story involving a collision of unimaginable scale. About 4.5 billion years ago, when the Earth was still young and molten, it likely shared its orbit with a Mars-sized planet that scientists have named Theia. In a chaotic game of cosmic billiards, Theia crashed into the Earth with tremendous force. The impact was so severe that it liquefied the surface of our planet and ejected a massive ring of debris into orbit. Over time, gravity did its patient work, gathering that dust and rock together to form the moon we see today. This violent birth explains why the moon is made of lighter materials similar to Earth's outer crust rather than its heavy iron core. It is essentially formed from the splash of that ancient impact. It's a strange thought that the serene light guiding us at night is actually a scar from a planetary collision, a beautiful reminder of a chaotic past that eventually settled into the rhythm of the tides. A quiet guardian born from the fire of two worlds becoming one. Far beyond our own moon, orbiting the ringed giant Saturn, lies a world that feels eerily like a frozen version of early Earth. This is Titan, Saturn's largest moon and the only moon in the solar system with a thick, substantial atmosphere. If you were to stand on its surface, bathed in a dim orange twilight, you would see rivers flowing into vast lakes, clouds drifting overhead, and rain falling from the sky. But this isn't water. The temperature on Titan hovers around 180 degrees below 0 Celsius, so cold that water is as hard as granite. Instead, the liquid cycle here is driven by methane and ethane, chemicals we use as gas on Earth, but which exist as liquids in Titan's deep freeze. The lakes, with names like Mare, are incredibly calm, mirroring the hazy sky above. The sheer strangeness of a world where water is rock and gas is liquid challenges our definitions of what a landscape can be. It is a place of familiarity and alien distortion, where the weather patterns we know so well play out with entirely different ingredients. A mirrored reality, frozen in time and shrouded in orange mist. While Titan holds its liquids on the surface, Jupiter's moon Europa hides its secrets deep underground. To the eye, Europa is a dazzling white ball of ice, crisscrossed by long, reddish-brown cracks that look like veins on a marble statue. It is the smoothest object in the solar system, lacking the deep craters found on other moons because its surface is constantly renewing itself. Beneath this frozen shell lies a global ocean of liquid water, kept warm not by the sun, but by the immense gravity of Jupiter. As Europa orbits, the giant planet pushes and pulls on the moon, flexing its core and generating heat through friction. This subsurface ocean is estimated to contain twice as much water as all of Earth's oceans combined. The cracks on the surface are likely places where the ocean vents or shifts the ice above. Scientists look to this hidden dark water as one of the most promising places to find life beyond Earth. It is a world where the habitat is a shell-encased womb, completely cut off from the stars, yet potentially teeming with activity in the crushing dark. A vast, silent sea waiting beneath a ceiling of ice. Another of Jupiter's moons, Io, offers a dramatic contrast to the frozen worlds of the outer solar system. It is the most volcanically active body we have ever discovered, a place where the ground is constantly turning itself inside out. Caught in a gravitational tug-of-war between the massive Jupiter and its sister moons Europa and Ganymede, Io is stretched and squeezed so violently that its interior melts. The result is a surface that looks like a mottled pizza, covered in sulfurous yellows, reds, and blacks. Volcanoes here don't just erupt occasionally. They are in a constant state of explosion, shooting plumes of sulfur and lava nearly 300 miles into space. The lava flows are so extensive that they erase any impact craters that might form, giving Io a strangely young surface despite its age. The ground itself rises and falls like a tide, heaving up and down by as much as 100 meters with every orbit. It is a hellscape of fire and brimstone, a testament to the sheer power of gravity to knead a solid moon into a ball of molten fury. A restless world that can never settle down, burning brightly in the shadow of a giant. Saturn possesses another wonder in the small, icy moon of Enceladus. For years, astronomers thought it was just another frozen block of ice, but the Cassini spacecraft revealed something breathtaking at its south pole. There, looking like claw marks scratched into the surface, are long fissures known as tiger stripes. From these cracks, great geysers of water vapor and ice particles shoot violently into space, creating a plume that towers over the tiny moon. Enceladus is essentially snowing on the universe. In fact, It ejects so much material that it is responsible for creating Saturn's earring, a faint, misty circle of ice dust that trails in the moon's wake. Beneath its icy crust lies a global ocean of salty water, heated by tidal forces similar to those on Europa. When the Cassini probe flew directly through these plumes, it tasted salt and organic compounds, the building blocks of life. It is a rare gift to see the interior of a world sprayed out into the cosmos, offering up its secrets without us having to dig. A generous moon, sharing its hidden waters with the empty dark. Neptune, the windy blue giant at the edge of our neighborhood, hosts a moon called Triton that marches to the beat of its own drum. Triton is unique among the large moons of the solar system because it orbits in the opposite direction of its planet's rotation, a movement known as a retrograde orbit. This strange behavior suggests that Triton was not born alongside Neptune, but was likely a wandering object from the Kuiper belt, a cousin of Pluto that strayed too close and was captured by Neptune's gravity billions of years ago. It is a captive king, forced into an orbital dance it didn't choose. Because of this opposing motion, tidal forces are slowly causing Triton's orbit to decay. It is spiraling inward, inch by inch. In the distant future, millions of years from now, it will likely be torn apart by Neptune's gravity, shattering into a spectacular ring system that will rival or even surpass Saturn's in beauty. Until then, it remains a frozen world of nitrogen ice and dark geysers, circling backwards against the flow of the solar system. A doomed wanderer, slowly falling into the embrace of its captor. Finally, we turn to the largest moon in the entire solar system, Ganymede. Orbiting Jupiter, this moon is so massive that it is actually larger than the planet Mercury. If it orbited the Sun directly instead of Jupiter, it would almost certainly be classified as a planet in its own right. But Ganymede's size isn't its only claim to fame. It is the only moon known to possess its own intrinsic magnetic field. Deep inside Ganymede, a molten iron core churns and spins, generating a magnetic bubble that protects its surface from the worst of the solar wind. This mini magnetosphere is strong enough to create auroras, glowing bands of light near its poles, similar to the northern lights on Earth. However, because Ganymede is embedded within Jupiter's own massive magnetic field, its auroras dance in a complex rhythm, rocking back and forth as the magnetic environment shifts. It stands as a planetary scale world demoted to the status of a satellite, yet holding onto the characteristics that usually belong to planets alone. A hidden giant disguised as a moon, shielding itself with its own magnetic heart. One of the most persistent images we have of space comes from cinema, where spaceships must dodge and weave through dense fields of tumbling rocks in the asteroid belt. The reality of this region, which sits between Mars and Jupiter, is far more spacious and serene than the movies suggest. The asteroid belt is incredibly vast, spanning millions of kilometers, and the material within it is spread so thinly that if you were standing on an asteroid in the middle of the belt, you likely wouldn't be able to see any other asteroids with your naked eye. The average distance between significant objects in the main belt is roughly 1 million kilometers, or nearly 3 times the distance between the Earth and the Moon. Space agencies like NASA don't even have to calculate complex evasion paths for probes flying through the belt. The odds of hitting something by accident are astronomically low. Despite containing millions of rocky bodies, the total mass of the entire asteroid belt is surprisingly small. It is estimated to be just 4% of the mass of our own moon. About 1/3 of that entire mass is contained within just one object, the dwarf planet Ceres. These rocky remnants are the leftovers from the solar system's formation, pieces that never quite coalesced into a planet because of Jupiter's immense gravitational interference. Instead of a chaotic, crashing hazard zone, the asteroid belt is a wide, empty highway where silent rocks orbit in isolation, separated by oceans of vacuum. Far beyond the orbit of Neptune, past the realm of the gas giants, lies a second, colder ring of debris known as the Kuiper Belt. While the asteroid belt is made mostly of rock and metal, the Kuiper Belt is a donut-shaped region populated by icy bodies, frozen volatiles like methane, ammonia, and water. This region is significantly larger than the asteroid belt, stretching for billions of kilometers into the dark. It is the home of Pluto, which was reclassified as a dwarf planet largely because we realized it was just one of many large, icy worlds drifting in this zone. Astronomers have found other massive objects here, like Eris, which is almost the same size as Pluto, and Haumea, which spins so fast it has been pulled into the shape of a flattened egg. These objects are incredibly old, pristine remnants from the very beginning of our solar system, effectively deep frozen in time for over 4 billion years. When the New Horizons spacecraft flew past Arakoth, a smaller Kuiper belt object, it revealed a gentle, reddish world formed by two lobes fusing together at a slow walking speed, proving that this distant region is a place of quiet preservation rather than violent collision. It is a graveyard of building blocks that never became planets, drifting slowly in the dim light of a distant sun. Surrounding our entire solar system like a massive, thick shell is a theoretical region called the Oort cloud, which marks the true, terrified edge of the sun's gravitational influence. Unlike the asteroid belt or the Kuiper belt, which are flat disks aligned with the planets, the Oort cloud is a sphere that encases us from all directions. It is immensely far away, starting roughly 2,000 times farther from the sun than Earth is, and extending perhaps halfway to the next nearest star, Proxima Centauri. This region is thought to be the reservoir for long-period comets, those icy wanderers that take thousands or even millions of years to complete one orbit. Occasionally, the gravity of a passing star or the tidal forces of the Milky Way galaxy itself will nudge one of these icy bodies, causing it to fall inward toward the sun. Because the Oort cloud is so distant, we have never actually seen objects inside it directly. It is too faint and far for even our best telescopes. We know it exists only by mathematical deduction and by tracing the paths of the comets that visit us. It is a ghostly, frozen wrapper around our home, containing trillions of icy objects drifting in the deepest cold imaginable, barely holding on to the sun's gravity. A silent, invisible barrier between us and the rest of the galaxy. When one of those icy bodies falls inward and gets close to the sun, it transforms into one of the most beautiful sights in the heavens, a comet. The spectacular tale that defines a comet is actually the result of a process called sublimation, where the sun's heat causes the ice on the comet's surface to turn directly into gas, skipping the liquid phase entirely. As this gas escapes, it drags dust particles with it, creating a vast cloud around the solid nucleus. What is fascinating is that a comet usually has two distinct tails that point in slightly different directions. One is a dust tail, which is white or yellowish and curves gently along the comet's path. The other is an ion tail, which glows with a faint blue light and is made of electrically charged gas. This blue tail always points directly away from the sun, regardless of which way the comet is moving, because it is being blown by the solar wind, a stream of charged particles flowing out from the star. The scale of these tails is difficult to comprehend. While the solid nucleus of a comet might be only a few kilometers wide, roughly the size of a city, the tail can stretch for hundreds of millions of kilometers, sometimes longer than the distance between the Earth and the Sun. It is a tremendous display of light and chemistry generated by a tiny, dirty snowball warming up in the sunlight. A fleeting, ethereal brushstroke across the night sky. Not all planets have the luxury of orbiting a star. There is a class of silent wanderers in our galaxy known as rogue planets. These are worlds that float untethered in the interstellar dark, orbiting the galactic center directly rather than circling a sun. Astronomers believe these planets likely formed within traditional solar systems, but were violently ejected during the chaotic early days of planetary formation, perhaps after venturing too close to a gas giant like Jupiter. Cast out by gravity, they travel through the freezing void of interstellar space. Surprisingly, they might not be completely dead worlds. A thick atmosphere could theoretically trap the heat generated by the planet's internal radioactive decay, potentially keeping the surface or subsurface warm enough for liquid water, even without sunlight. Recent studies suggest that these nomadic worlds might be incredibly common. Some estimates indicate there could be more rogue planets in the Milky Way than there are stars. They drift alone through the vast distances between solar systems, invisible to our eyes because they reflect no starlight, revealing themselves only when their gravity briefly magnifies the light of a background star. They are the galaxy's silent travelers, moving through the eternal night without a sunrise to mark the passage of time. In late 2017, humanity realized for the first time that we were being visited by an object that did not belong to our solar system at all. This object was named Oumuamua, a Hawaiian word roughly translating to a messenger from afar arriving first. Unlike the asteroids and comets we are used to, Oumuamua had an extremely unusual trajectory and speed, indicating it had come from interstellar space and was just passing through. As it tumbled through our neighborhood, astronomers scrambled to observe it, discovering it was reddish in color and had a bizarre, elongated shape, often compared to a cigar or a flat pancake, potentially 10 times longer than it was wide. This shape is unlike anything seen naturally in our own system. Even more mysteriously, as it moved away from the sun, it accelerated slightly faster than gravity alone would allow. While this was likely due to the rocket effect of unseen gas venting from its surface as it warmed, the absence of a visible tail puzzled scientists. Oumuamua swung past the sun and is now heading back out into the void, moving too fast for us to ever catch. It offered us a brief, tantalizing glimpse of the material that exists in other star systems, a momentary greeting from the deep cosmos before vanishing into the dark forever. The speed of light is the absolute speed limit of the universe, a constant that dictates how we perceive reality itself. Light travels at approximately 300,000 kilometers every single second. While this sounds incredibly fast, fast enough to circle the Earth 7.5 times in a single heartbeat, it is surprisingly slow when measured against the vastness of the cosmos. Because space is so enormous, light acts less like an instant messenger and more like a slow-moving carrier pigeon. It takes light about 8 minutes to travel from the sun to your skin. It takes 4 years to reach us from the next nearest star, Proxima Centauri. And to cross the Milky Way galaxy from one edge to the other takes light over 100,000 years. This speed limit means that there is a fundamental delay in everything we see. We never see the universe as it is right now. We only see it as it was. When you look at the moon, you are seeing it as it was 1.3 seconds ago. When you look at Mars, you might be seeing it as it was 20 minutes ago. We live in a bubble of the now, but everything outside that bubble is an echo from the past, arriving on a delay that grows longer the further we look. It is a reminder that in space, distance and time are effectively the same thing, woven together in a fabric that separates us from the rest of existence. A message bottle floating across the cosmic ocean. Because of this travel time, powerful telescopes act as genuine time machines that allow us to witness history unfolding. When astronomers point the Hubble or James Webb Space telescopes at a dark patch of sky, they are looking deep into the well of time. The light from the Andromeda galaxy left its source 2.5 million years ago, long before modern humans walked the earth, meaning that when you see it through a telescope, you are seeing a version of the galaxy that is older than our entire species. If we look even further, at galaxies billions of light years away. We can see them as they were in their infancy, chaotic and unformed, shortly after the universe began. This creates a strange paradox where the farthest things we can see are also the youngest things we can see. We cannot see these distant galaxies as they are today. For all we know, they may have merged, faded, or changed entirely. But that news hasn't reached us yet. The light carrying that information is still traveling through the void, making its long, lonely commute across the universe. It allows us to piece together the life story of the cosmos by looking at different epochs simultaneously, layered over one another in the sky. We are surrounded by ghosts of the past, their ancient light finally finding a place to land. As light travels through the expanding universe, it undergoes a transformation known as redshift, which is similar to the way a siren's pitch drops as an ambulance drives away from you. When a light source, such as a distant galaxy, moves away from us, the light waves it emits get stretched out. As the wave stretches, it shifts toward the red end of the color spectrum, which has longer wavelengths. In the 1920s, Edwin Hubble noticed that almost all galaxies were redshifted, meaning they were all moving away from us. Even more surprisingly, the farther away a galaxy was, the more its light was stretched, indicating it was moving away faster. This wasn't because the galaxies were flying through space like rockets, but because space itself was expanding between them, stretching the light as it traveled. The most distant objects in the universe have been moving away from us for so long that their light has been stretched beyond the visible red spectrum entirely and has become infrared light. This is why we need special infrared telescopes to see the earliest stars. Their visible light has been pulled like taffy by the expansion of the cosmos until it became heat radiation. It is the color of a long farewell, stretching out over billions of years. Gravity has the power to bend light, creating a phenomenon known as gravitational lensing that turns the universe into a giant magnifying glass. According to Einstein's general relativity, massive objects like clusters of galaxies warp the fabric of space around them. When light from a more distant object passes near this massive cluster, it follows the curve of space, bending around the obstacle. This bending of light can magnify the distant background object, allowing us to see galaxies that would otherwise be too faint or too far away to detect. Sometimes the alignment is so perfect that the background background galaxy is warped into a complete circle of light known as an Einstein ring. It's like looking through the bottom of a wine glass. The image is distorted and stretched, but it is also brighter and larger. Astronomers use these natural cosmic lenses to peer deeper into the universe than their technology would normally allow. Using the gravity of massive galaxy clusters to boost the power of their telescopes. It turns the obstacles of space into tools of discovery, revealing hidden treasures behind the curtain of gravity. A funhouse mirror reflecting the secrets of the deep. We can determine exactly what stars and planets are made of without ever visiting them, thanks to a technique called spectroscopy. When light from a star passes through a prism, it spreads out into a rainbow of colors called a spectrum. But if you look closely at that rainbow, you will see thin, dark lines appearing at very specific intervals, looking almost like a supermarket barcode. These are absorption lines, and they are caused by different chemical elements in the star's atmosphere, absorbing specific wavelengths of light. Every element in the periodic table, hydrogen, helium, carbon, iron, has a unique barcode. By reading these lines, astronomers can identify the chemical composition of an object billions of light years away with incredible precision. This is how we know the universe is made of the same stuff we are. We can even use this on exoplanets. As a planet passes in front of its star, the starlight filters through the planet's atmosphere, and the resulting spectrum tells us if there is water, methane, or oxygen in that alien air. It turns a single point of light into a detailed chemical report, bridging the impossible distances with information. A way to touch the stars through the language of color. The universe is occasionally illuminated by gamma ray bursts, which are the most energetic electromagnetic events known to occur since the Big Bang. These flashes of high-energy light can last anywhere from a few milliseconds to several minutes. But in that brief window, a single burst can release more energy than our sun will emit in its entire 10 billion year lifetime. They are thought to be caused by the dramatic death of massive stars collapsing into black holes, or by the collision of two dense neutron stars. The energy is not released in a sphere, but in narrow, focused jets, like a cosmic lighthouse beam sweeping across the dark. If Earth were to be hit directly by a gamma ray burst from a nearby star, it would strip away our ozone layer and cause a mass extinction. But Unfortunately, these events are usually detected coming from galaxies billions of light years away. They serve as beacons across the cosmos, marking the violent end of one thing and the creation of something new, like a black hole. They are reminders of the immense power hidden in the fabric of matter, capable of outshining an entire galaxy of stars before fading back into the silence. A momentary shout that echoes across the dark ages. There is a vast amount of light in the universe that our human eyes cannot see, and radio astronomy allows us to listen to this invisible cosmos. Visible light makes up only a tiny fraction of the electromagnetic spectrum. The universe is awash in radio waves, which are just like light waves, but with much longer wavelengths, some as long as a football field. When astronomers look at the sky with radio telescopes, which look like giant satellite dishes, the familiar constellations disappear, replaced by a completely different landscape. They see clouds of cold gas where future stars will be born, the rapid pulsing of spinning neutron stars, and the faint, ancient static left over from the Big Bang itself. In the radio spectrum, the sky is never dark. It is glowing with energy and activity. The supermassive black hole at the center of our galaxy, which is invisible to our eyes, shines brightly in radio waves. By tuning into these frequencies, we essentially give ourselves new senses, allowing us to perceive the hum of the universe that has been playing silently around us for all of human history. It reveals that the quiet night sky is actually filled with a constant, complex song of energy, the hidden melody of existence. When we look up at the night sky, we naturally assume that what we see is what exists. We see the bright pinpoints of stars, the glowing trails of the Milky Way, and the wandering planets reflecting the light of the sun. It feels substantial and complete. However, one of the most humbling discoveries of modern astronomy is that everything we can see, every star, every galaxy, every cloud of gas, and every atom in your body makes up only about 5% of the universe. The rest is hidden in the dark. This normal matter, which physicists call baryonic matter, is essentially just the foam on top of a deep, invisible ocean. About 27% of the cosmos consists of something called dark matter, a substance that doesn't emit or reflect light and passes right through ordinary objects. The remaining 68% is even more mysterious, a force known as dark energy that pushes space itself apart. This means that if you were to look at the universe as a pie, the slice representing everything we have ever known, seen, touched, or loved is just a tiny sliver. The vast majority of reality is composed of substances and forces that we cannot see and can only detect by their gravitational effects on the things we can see. It changes the way we think about our place in the cosmos. We are not the main structure of the universe. We are merely the rare, luminous decoration scattered across a vast, invisible scaffolding. It suggests that the true nature of reality is silent and unseen, a ghost world that holds our visible world in its hands, shaping our destiny without ever revealing its face. The existence of this invisible framework was first strongly suggested by the astronomer Vera Rubin in the 1970s through her observation of how galaxies rotate. Before her work, astronomers expected galaxies to behave somewhat like our solar system. In our solar system, the planets closest to the Sun, like Mercury, orbit very quickly because they feel the strongest gravitational pull. The planets farther out, like Neptune, move much more slowly, drifting lazily through their wide orbits. Scientists assumed galaxies would follow the same rules. Stars near the dense, bright center should whip around at high speeds, while stars at the sparse outer edges should move slowly. But when Vera Rubin and her colleague Kent Ford measured the speeds of stars in the Andromeda galaxy and others, they found something impossible. The stars at the chaotic outer edges were moving just as fast as the stars near the center. By all laws of physics known at the time, these outer stars were moving so fast that they should have been flung out into deep space, like a car taking a corner too quickly. But they didn't fly away. They held their orbits. Rubin realized that for these galaxies to hold together at such speeds, there had to be an enormous amount of extra mass, providing extra gravity, mass that we couldn't see. She calculated that a galaxy must be embedded in a vast sphere or halo of invisible matter that outweighs the visible stars by 10 to 1. It was as if she had discovered that the visible galaxy was just the brightly lit window of a much larger, darker building. Her work provided the first robust evidence for dark matter, proving that what we see is only a fraction of what is there, held together by an invisible grip that prevents the stars from scattering into the void. While dark matter pulls things together, the other major component of the invisible universe, dark energy, is busy pushing them apart. For most of the 20th century, the prevailing belief was that the expansion of the universe, which began with the Big Bang, would eventually slow down. The logic was simple. Gravity attracts. With all the galaxies pulling on each other, their mutual gravity should act like a brake on the universe's expansion, eventually bringing everything to a halt, or even reversing it into a big crunch. But in the late 1990s, two teams of astronomers studying distant supernovae found the exact opposite. They looked at specific types of exploding stars that serve as cosmic mile markers, allowing them to measure distances across space and time. What they found shocked the scientific community. The expansion of the universe isn't slowing down at all. It is accelerating. The galaxies are rushing away from each other faster today than they were in the past. It is as if you threw a ball into the air, and instead of slowing down as it rose, it suddenly strapped on a rocket engine and sped off into the sky. This accelerating force is what we call dark energy. It acts like a kind of anti-gravity, a repulsive pressure inherent in empty space itself. As the universe expands and creates more space, it creates more dark energy, which in turn pushes the expansion faster. It implies a lonely future for the cosmos. Billions of years from now, this force will have pushed other galaxies so far away that they will disappear from our view entirely, moving faster than their light can reach us, leaving our galaxy alone in an ocean of absolute blackness. This mysterious expansive force brings us back to an idea that Albert Einstein once had, then discarded, then found redeemed decades after his death. When Einstein was formulating his general theory of relativity, he found that his equations predicted a dynamic universe, one that was either expanding or contracting. At the time, however, the scientific consensus was that the universe was static and unchanging, eternal and still. To make his math match this belief, Einstein added a term to his equations called the cosmological constant, represented by the Greek letter lambda. This constant acted as a counterforce to gravity, holding the universe still so it wouldn't collapse under its own weight. A few years later, when Edwin Hubble discovered that the universe was actually expanding, Einstein famously realized his error, calling the cosmological constant his biggest blunder. He removed it from his equations, assuming it was a mistake born of a desire for a steady universe. But when dark energy was discovered in the 1990s, physicists realized that Einstein's blunder was actually the perfect description for this new force. The cosmological constant represents the energy density of empty space, the idea that a vacuum isn't truly nothing, but has an intrinsic energy that pushes outward. It turns out that nothing weighs something. Even if you remove every atom, every particle, and every ray of light from a box, the empty space remaining inside still has this energy. And because the universe is mostly empty space, this energy dominates everything else. It is a beautiful irony that a mathematical patch, invented to keep the universe still, is actually the engine that drives its runaway motion. We can also see the fingerprints of the dark universe in the subtle patterns of galaxies, specifically through something called baryon acoustic oscillations. This complicated name describes a very simple and poetic phenomenon: sound waves from the beginning of time. In the very early universe, long before stars or galaxies formed, the cosmos was a hot, dense soup of plasma, a mixture of matter and light. Because it was so dense, sound waves could travel through it, created by the interplay of gravity pulling inward and radiation pressure pushing outward. These pressure waves rippled through the infant universe like sound traveling through air or ripples spreading in a pond. They traveled for about 380,000 years. Then, as the universe expanded and cooled, the plasma turned into neutral gas, and the light was set free. At that moment, the sound waves effectively froze in place. They didn't disappear. They left a permanent imprint on the distribution of matter. The ripples created slightly denser regions where the waves stopped, and over billions of years, gravity pulled more matter into these denser shells. Today, we see the result. Galaxies are not scattered randomly, but tend to cluster in spheres separated by a specific distance, directly corresponding to those ancient sound waves. Astronomers use this distance as a standard ruler to measure the geometry of the universe. When we look at the arrangement of galaxies millions of light years away, we are essentially looking at the frozen echoes of a primordial song that rang out when the universe was born. It is a harmonious pattern hidden in the chaos, a reminder that the structure of the vast cosmos was determined by the physics of sound in a time before silence. While dark matter and dark energy are the heavyweights of the invisible universe, there is another ghostly particle that is far more common, yet incredibly difficult to catch: the neutrino. These are subatomic particles that are nearly massless and have no electric charge. because they don't feel the electromagnetic force. They don't interact with normal matter in the way other particles do. They don't bounce off atoms or stick to them. They simply pass through. Right now, at this very second, about 100 trillion neutrinos are passing through your body. They come primarily from the sun, produced in the nuclear fusion reactions at its core. They stream out from the solar center, cross the 93 million miles of space, and arrive at Earth in just 8 minutes. But unlike sunlight, which stops at your skin or the roof of your house, neutrinos keep going. They pass through your roof, through you, through your bed, through the floor, and travel all the way through the entire planet Earth, exiting the other side and continuing into space as if the Earth weren't even there. To a neutrino, a planet is mostly empty space. To detect them, scientists have to build massive observatories deep underground, like the Super Kamiokande in Japan, which is a giant tank filled with 50,000 tons of ultra-pure water. They bury it deep in a mine to shield it from other cosmic rays. They wait for the exceedingly rare moment when a single neutrino happens to collide head-on with an atomic nucleus in the water, creating a tiny flash of blue light. It is a quiet, patient vigil for a particle that outnumbers atoms in the universe by 1,000,000,000, yet touches almost nothing. A flowing river of ghosts that washes over us constantly, connecting us to the heart of the sun without us ever feeling a thing. When we look at the most spectacular images of the cosmos, the vibrant clouds of color and light that capture our imagination are almost always nebulae. Yet, for all their complex beauty, these celestial masterpieces are constructed from the simplest ingredients in existence. A nebula is primarily composed of hydrogen, the most basic element in the universe, along with a smaller amount of helium and just a dusting of heavier elements. The breathtaking reds, greens, and blues we see in telescope images are actually the signatures of these specific elements interacting with starlight. For instance, when hydrogen gas is energized, it glows with a distinct red hue, while oxygen often appears as a ghostly blue-green. It is a remarkable paradox that the universe creates its most intricate visual art using its most basic supplies. These clouds can be hundreds of light years across, serving as both the graveyards of old stars and the nurseries of new ones. The material inside them is often the debris blown off by dying suns, drifting through the dark until gravity pulls it together again to start the cycle anew. In a way, nebula is a cosmic pause between one generation of stars and the next, a colorful waiting room where matter is reshaped and repurposed. It is a quiet reminder that in the natural world, nothing is ever truly wasted, and even the simplest floating gas can become something magnificent if given enough time and space to shine. One of the most iconic structures in the night sky is a specific formation within the Eagle Nebula known as the Pillars of Creation. These towering columns of gas and dust look like ancient stalagmites rising from the floor of a cave, but their scale is almost impossible to comprehend. The tallest pillar stretches roughly 4 light years into space, meaning that if you could travel at the speed of light, it would take you 4 years just to travel from its base to its tip. To put that in perspective, the entire span of our solar system is tiny compared to just a small section of one of these pillars. Despite their solid, rock-like appearance in photographs, these structures are actually made of cold, shifting gas that is slowly being eroded by the intense ultraviolet light from nearby newborn stars. It is a slow-motion destruction where the very stars that the nebula birthed are now carving away their own cradle. Astronomers believe that a supernova shockwave may have actually toppled these pillars thousands of years ago. Because light takes 7,000 years to travel from the Eagle Nebula to Earth, we are still seeing them as they were before the destruction arrived. We are watching a ghost, admiring a structure that may no longer exist, its image carried across the vast ocean of time to reach our eyes. A memory made of light, still standing tall in the quiet dark. Not all nebulae glow with their own light. The difference lies in their relationship with the stars around them. Astronomers distinguish between 2 main types, emission nebulae and reflection nebulae. An emission nebula is like a neon sign. There is a hot, young star nearby releasing so much energy that it strips electrons from the surrounding gas atoms, causing the gas itself to glow. The Orion Nebula is a classic example of this, radiating its own light into the void. In contrast, a reflection nebula is more like fog around a street lamp. It contains dust grains that don't emit their own light, but instead scatter the light from nearby stars. This scattering effect is the same physics that makes our sky blue here on Earth, which is why reflection nebulae often appear in soft, ghostly shades of blue. The Pleiades star cluster, often called the Seven Sisters, is wrapped in this kind of delicate, reflective veil. It creates a scene of immense tranquility where the dust isn't burning or reacting, but simply catching the light of its neighbors and casting it back out into the universe. It shows us that you don't always need to generate your own energy to be seen. Sometimes just being near something bright is enough to create a spectacle of soft, scattered radiance. The density of these cosmic clouds is one of the most counterintuitive facts in astrophysics. When we see a nebula in a photograph, it looks thick and opaque, like a heavy storm cloud rolling over a mountain range. You might imagine that if you flew a spaceship into one, you would be surrounded by a dense fog, unable to see the stars beyond. However, the reality is that nebulae are incredibly tenuous, fainter than the finest mist. In fact, the thickest parts of a nebula are actually a stronger vacuum than anything we can create in a laboratory on Earth. If you were physically inside a nebula, you might not even realize it. The gas and dust are so spread out that the region would look almost entirely empty to the human eye. The only reason they look like solid clouds to us is that they are astronomically huge. We are looking through billions of miles of this incredibly thin material. And over that vast distance, the tiny number of atoms adds up to block the light and create the appearance of a solid form. It is an illusion of scale. The universe can create the appearance of heavy, substantial structures simply by layering almost nothing over an expanse of almost forever. It teaches us that solidity is often just a matter of perspective, and that even the emptiest spaces can hold a shape if you look at them from far enough away. Between the distinct nebulae and the bright stars lies something called the interstellar medium, or ism. We often think of space as a perfect void, a complete nothingness between solar systems, but this is not quite true. The space between stars is filled with a very thin soup of gas, dust, and cosmic rays. It acts like the atmosphere of the galaxy, a reservoir of matter that is constantly flowing and changing. While the density is incredibly low, often just one atom per cubic centimeter, the sheer volume of space means that the interstellar medium accounts for a significant portion of the galaxy's total mass. This medium is where the sounds of the universe would live if there were ears to hear them. While sound, as we know it, cannot travel through the vacuum, pressure waves can and do move through these thin gases, rippling outward from explosive events like supernovae. These waves can travel for millions of years, gently compressing the gas clouds they encounter. This compression is often the spark that triggers gravity to take over, collapsing the cloud to form new stars. The interstellar medium is the connector, the subtle fabric that ties every star system together. It ensures that no star is truly an island, but rather a point of light floating in a vast, invisible ocean that gently touches everything else. The transition from these vast clouds of gas to solid, rocky worlds like our own is a story of dust. Cosmic dust is not like the dust under your bed. It consists of tiny grains of carbon, silicon, and ice, smaller than the width of a human hair. In the early life of a solar system, these grains orbit a young star in a flat disk. The mystery for a long time was how these tiny specks could ever come together to form massive planets. Gravity is too weak to pull individual dust grains together. The answer lies in something much gentler: static electricity. Just as dust bunnies clump together on a hardwood floor, cosmic dust grains drift past each other and stick due to weak electrostatic forces. Slowly, patiently, these tiny clumps grow into pebbles, then into boulders. Once they reach a certain size, about a kilometer across, their gravity finally becomes strong enough to pull in more material, and the process accelerates. It is a chaotic yet constructive dance that turns microscopic soot into mountains, oceans, and continents. Every rock you have ever held, every mountain you have ever climbed, and indeed the earth itself, began as scattered dust floating in the silence of a nebula. It is a comforting thought that the ground beneath us is made of the same drifting material as the dark clouds that obscure the stars, anchored now by gravity and time. One of the most surprising realizations in physics is just how incredibly weak gravity actually is compared to the other forces. We tend to think of gravity as a dominant, crushing power because it keeps our feet on the ground and holds the moon in orbit. But in the grand hierarchy of nature, it is essentially a whisper. You can prove this relative weakness with a simple kitchen magnet. A tiny piece of metal, the size of a coin, can lift a paper clip off the table, completely overcoming the gravitational pull of the entire planet Earth. The electric and magnetic forces involved in that small interaction are roughly 1 billion trillion times stronger than the gravitational force pulling the paperclip down. Gravity is so faint that physicists still struggle to understand why it is the odd one out, leading to theories that perhaps gravity leaks away into other dimensions we cannot see. However, gravity has a unique advantage that allows it to rule the cosmos. It is cumulative and always attractive. While electrical charges usually cancel each other out, positive meeting negative to create neutrality, gravity just adds up. Every atom in a planet contributes to the total pull, building a force massive enough to crush rock and ignite stars. It is the patient architect of the universe, working slowly over billions of years, gathering dust and gas until the sheer weight of matter creates the fires of the heavens. A force that is individually negligible, yet collectively omnipotent. While gravity shapes the large-scale structure of the universe, the force of electromagnetism is responsible for almost everything we experience in our daily lives. This force governs the interaction between electrically charged particles, and it is the reason that light exists at all. Light, in all its forms, from the radio waves carrying music to the warmth of infrared and the colors of a sunset, is simply a vibration in the electromagnetic field. This force is what prevents you from falling through your bed right now. The electrons in the atoms of your body repel the electrons in the atoms of the mattress with a force strong enough to support you. In the vacuum of space, electromagnetism plays a different but equally vital role. It is the messenger of the cosmos, because electromagnetic waves can travel forever through the void without losing their identity. They allow us to see objects billions of light years away. A photon created in the heart of a distant star can travel for millions of years, dodging dust clouds and navigating the emptiness, only to end its journey by hitting the retina of your eye. Without this force, the universe would be invisible and silent, with no way for information to travel between the stars. It connects the observer to the observed, weaving a web of light that stretches across the entire observable history of creation. A bridge of light spanning the dark. Deep within the heart of matter, far smaller than the reach of light or gravity, lies the strong nuclear force. This is the glue that holds reality together at its most fundamental level. In the nucleus of an atom, protons are packed tightly together, but because they all carry a positive electric charge, they naturally want to repel each other with tremendous violence. If only electricity ruled, every atomic nucleus would instantly explode apart the universe would be nothing but a soup of loose particles. The strong nuclear force overpowers this electrical repulsion, clamping the protons and neutrons together with an intensity that is unmatched by any other force in nature. However, it is remarkably short range, operating only across distances about the size of a solitary proton. It is like a powerful Velcro that only sticks when the pieces are touching. This force is also the engine of the stars. When gravity crushes hydrogen atoms together in the core of the sun, it is the strong force that finally snaps them together into helium, releasing the energy that bathes our solar system in light. Every beam of sunlight you have ever felt is a direct result of this microscopic binding taking place 93 million miles away. It is a hidden strength, silent and invisible, preventing all matter from unraveling into dust. Working alongside the strong force is the weak nuclear force, which is responsible for the alchemy of the universe. While the strong force binds things together, the weak force allows them to change. It is the only force capable of changing one type of subatomic particle into another, effectively allowing protons to turn into neutrons. This might sound like a minor technical detail, but without this ability, the sun would not shine. For nuclear fusion to occur, hydrogen must eventually become helium, a process that requires this fundamental transformation of particles. The weak force is also the driver of radioactive decay, the process by which unstable atoms break down over time, releasing energy as they seek a more stable state. This decay deep within the Earth generates the heat that keeps our planet's core molten, driving the movement of continents and creating the protective magnetic field that shields us from solar radiation. It is a force of transformation and transition, operating on time scales that can range from a fraction of a second to billions of years. It reminds us that matter is not static, but fluid and mutable, capable of changing its very identity under the right conditions. A quiet agent of change in a universe that appears solid. We often think of space as simply an empty stage where events happen, but general relativity teaches us that space is a physical fabric. This fabric, which physicists call space-time, is not a passive background, but a dynamic participant in the cosmic dance. Imagine a heavy bowling ball placed on a trampoline. It curves the fabric downwards, If you roll a marble across the trampoline, it will curve around the bowling ball, not because there is a magical force pulling it, but because it is following the curve of the surface itself. In the same way, massive objects like stars and galaxies warp the geometry of space and time around them. Earth doesn't orbit the sun because the sun is pulling on it. Earth is simply moving in a straight line through a space that has been curved by the sun's mass. This curvature affects time as well as space. The stronger the gravity, the slower time moves. This means that time passes slightly faster for an astronaut in orbit than it does for you on the ground, and significantly slower near the surface of a black hole. We are not just moving through space, we are navigating a landscape of invisible hills and valleys made of geometry itself. We are travelers on a surface we cannot see, guided by the shape of the nothingness around us. Even the emptiest regions of the universe, where there are no stars, no dust, and no light, are not truly empty. According to quantum mechanics, the vacuum of space is a seething ocean of activity. This is known as the quantum vacuum or quantum foam. In this microscopic realm, the laws of conservation of energy allow for a strange loophole. Energy can be borrowed from nowhere as long as it is paid back almost instantly. This manifests as virtual particles, pairs of matter and antimatter that pop into existence, exist for a fleeting fraction of a second, and then collide and annihilate each other, vanishing back into the void. This means that every cubic centimeter of empty space is actually alive, with a constant, bubbling static of creation and destruction. These fluctuations are incredibly small, but their effects can be measured in laboratories, and they may be responsible for the very origin of the universe itself. Many cosmologists believe that the Big Bang began as a random quantum fluctuation that rapidly expanded, freezing these tiny ripples into the large-scale structure of galaxies we see today. The silence of the void is an illusion. Underneath the quiet, the universe is humming with a ceaseless, invisible energy, a restless sleep that dreams of existence. The combination of all these forces, gravity, electromagnetism, and the nuclear interactions, leads some scientists to a startling hypothesis: the multiverse. Our universe seems to be fine-tuned for life. If the strong nuclear force were just slightly weaker, atoms would never form. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. This precision is a deep mystery. One solution is that our universe is just one bubble in a vast, foaming sea of other universes, each with its own set of physical laws. In this eternal inflation scenario, the Big Bang was not a unique event, but a common occurrence, happening continuously like bubbles rising in a pot of boiling water. In some of these other universes, gravity might be repulsive, or light might not exist, or matter might never coalesce into stars. We find ourselves in this specific universe simply because it is one of the few capable of supporting observers to ask the question. While we cannot see or touch these other realities, the mathematics of string theory and inflation suggest they could exist, separated from us by the impassable bulk of higher dimensions. It suggests that our entire cosmic history is just a single note in a symphony of infinite variations. A humbling thought that places our reality as one among many. When we speak of the universe, our human words for distance often fail to capture the true scale of what lies above. We rely on terms that blend time and space together because, out there, they are effectively the same thing. The most famous of these measurements is the light year, a phrase that sounds like a measure of time, but is actually a ruler of immense length. A single light year is the distance that a beam of light, moving at its cosmic speed limit, can travel in one Earth year. Since light races through the vacuum at about 300,000 kilometers every single second, the distance it covers in a full year is staggering, roughly 9.5 trillion kilometers. To put that into a perspective that makes sense to our daily lives, if you were to board a commercial jetliner flying at cruising speed, it would take you over 1,000,000 years to travel just one light year. Yet, in the grand layout of the cosmos, this is a tiny step. Our nearest stellar neighbor, Proxima Centauri, sits just over 4 light years away, meaning the light we see from it tonight actually left the star whilst we were living 4 years in the past. This creates a strange and beautiful reality where looking up at the night sky is actually an act of looking back in history. The deeper we look, the older the image. We never see the universe as it is right now. We only see it as it was. It is a gallery of ghosts and echoes, shimmering across a gulf so wide that the light takes lifetimes to bridge it. While the light year is poetic, professional astronomers often prefer a tool that relies on geometry and perspective called the parsec. This unit of measurement, which equals about 3.26 light years, is born from a clever trick of navigation called parallax. You can understand this concept just by holding your thumb out at arm's length and closing one eye, then the other. Notice how your thumb seems to jump sideways against the background. That shift is parallax. Astronomers use the Earth's orbit around the Sun as the distance between their eyes. By measuring the position of a nearby star in January and then measuring it again in July when Earth is on the opposite side of the Sun, they can see a tiny shift in that star's position against the backdrop of much more distant stars. The parsec is defined by the mathematics of that tiny angle. It turns the entire orbit of our planet, a circle 300 million kilometers wide, into a mere baseline for a triangle that stretches out to the stars. It is a testament to human ingenuity that we can measure the infinite simply by observing how our own viewpoint changes as we drift through the seasons. It reminds us that sometimes, to understand how far away something is, you simply need to look at it from a different perspective. A shift in view that turns the flat sky into a deep, three-dimensional ocean. To truly grasp the age of the universe compared to our own brief existence, scientists often use the analogy of the cosmic calendar. Imagine compressing the entire 13.8 billion year history of the universe into a single calendar year, starting with the Big Bang as the first second of January 1st. In this scale, every month represents a little over 1 billion years, and every day represents about 40 million years. For the first few months of this cosmic year, the universe is a chaotic, forming place. Our own Milky Way galaxy doesn't even begin to form until March. But our specific home is a late arrival. Our sun and solar system don't spin into existence until the very end of August. Life on Earth begins as simple microscopic whispers in late September. The dinosaurs, which seem so ancient to us, don't stomp across the planet until Christmas week, dominating the globe for 5 days before vanishing on December 30th. And where are we in this vast timeline? We humans only emerge in the final moments of New Year's Eve. Recorded history, every king, war, invention, and story we have ever known occupies only the last 14 seconds of the year, right before the clock strikes midnight. It is a humbling compression of time that shows us how young we truly are. We are the newest guests at a very old party, just now waking up to look around the room. One of the most mind-bending discoveries in physics is that time itself is not a constant, steady ticking clock, but a river that flows at different speeds depending on how you move. This phenomenon, known as time dilation, means that the faster you travel through space, the slower you move through time relative to someone standing still. It sounds like science fiction, but it is a measured reality that affects the technology we use every day. The satellites that power the GPS on your phone orbit the Earth at high speeds, roughly 14,000 kilometers per hour. Because of this speed, their onboard atomic clocks tick slightly slower than clocks on the ground, a difference of mere microseconds, but enough that if engineers didn't correct for it, your map location would be off by kilometers within a single day. If you were to board a hypothetical spaceship that could travel near the speed of light, this effect would become extreme. You might travel to a distant star and back in what feels like a few years to you, only to return and find that decades or centuries have passed on Earth. Everyone you knew would have aged while you remained young. It implies that time is personal, a private experience dictated by your journey through the cosmos. A flexible ribbon that stretches and compresses, binding us to the speed of our own motion. There is another law of time that seems to govern the direction of everything, a concept known as entropy, or the arrow of time. In our experience, time only flows one way forward. We can remember the past, but we cannot remember the future. This directionality is driven by the universal tendency for things to move from order to disorder. Think of a hot cup of tea left on a table. The heat energy is concentrated in the liquid, representing a state of order. Over time, that heat naturally spreads out into the room until the tea is lukewarm, indistinguishable from the air around it. The energy has become disordered, and the tea will never spontaneously heat itself up again by gathering that warmth back from the air. This process is happening to the entire universe on a grand scale. Stars are burning their fuel, radiating heat into the cold vacuum, slowly spreading energy out until it is evenly distributed. This constant slide from concentrated energy to scattered energy creates the distinction between before and after. It is the reason glass shatters but does not reassemble, and why we age but do not grow younger. It is the subtle, drifting current that carries us all downstream. A quiet rule that ensures every moment is unique, never to be repeated in exactly the same way again. Within this vast expanse of time and distance, astronomers search for specific regions where life might flourish. areas affectionately known as Goldilocks zones. This is the narrow band around a star where the temperature is just right, not too hot and not too cold, allowing liquid water to exist on the surface of a planet. It is a delicate balance. If a planet is too close to its star, like Venus, any water boils away into steam, creating a thick, choking atmosphere. If it is too far, like Mars, the water freezes into ice, locking away the potential for chemistry. But the Goldilocks zone isn't a fixed distance. It depends entirely on the star. For a massive, blazing blue star, the habitable zone is far out, at a distance that would dwarf our solar system. For a small, cool red dwarf star, the zone is huddled close in, so close that a planet might race around its sun in just a few days. We are finding that these zones are common, yet holding onto that balance is rare. It requires not just the right distance, but the right atmosphere, the right protection, and the right history. It highlights how fortunate our position is, a perfect orbit in a quiet corner of the galaxy, suspended in a fragile equilibrium that has held steady for billions of years. A warm, blue oasis floating in the vast, dark distance. The most widely accepted theory for how the universe ends is actually a slow, quiet fade into silence, known as the heat death, or the big freeze. This scenario is based on the second law of thermodynamics, which tells us that entropy, or disorder, always increases in a closed system. Right now, the universe is full of concentrated energy sources like stars, which pour light and heat into the colder emptiness of space. But eventually, this flow of energy will try to balance itself out, like a cup of hot tea cooling down until it matches the temperature of the room. Over trillions and trillions of years, stars will burn through their fuel and cease to shine, and the gas clouds needed to form new stars will simply run out. Galaxies will drift so far apart due to the expansion of space that their light will no longer reach one another, leaving each island of stars in total isolation. As the last embers of the stellar furnaces fade, the universe will become a vast, cold, and uniform bath of low-level radiation, hovering just above absolute zero. In this state, no work can be done, no life can exist, and time effectively loses its meaning because nothing ever changes. It is not a violent ending, but rather a gentle settling into eternal rest. A quiet equilibrium where the fire of creation finally sleeps. In contrast to the cold silence of the heat death, there is a theory known as the Big Crunch, which suggests the universe might one day reverse its course. This idea depends heavily on the total density of matter in the cosmos and the ongoing battle between the outward push of expansion and the inward pull of gravity. If gravity eventually wins, the expansion of the universe will slow down, come to a halt, and then begin to contract. Imagine watching a movie of a firework exploding, but played in reverse. Distant galaxies would begin to race toward us rather than away, and the night sky would grow increasingly bright as the light from billions of stars gets compressed into smaller and smaller spaces. As the universe shrinks, the ambient temperature would rise dramatically, eventually becoming so hot that stars would vaporize and atoms would break apart. Ultimately, all matter, energy, and space-time would be crushed back into a single, infinitely dense point, a singularity similar to the one that started the Big Bang. Some physicists propose that this wouldn't be the true end, but rather the prelude to a big bounce, where the universe expands again in a new cycle of creation. A cosmic heartbeat, expanding and contracting through eternity. A third possibility, and perhaps the most dramatic, is a scenario called the Big Rip, driven by the mysterious force of dark energy. Currently, dark energy is causing the expansion of the universe to accelerate, pushing galaxies away from each other. In the Big Rip scenario, the strength of this dark energy increases over time, eventually becoming so powerful that it overwhelms gravity entirely. The process would begin with galaxies being torn apart, their stars scattered into the void, because the gravity holding the galaxy together can no longer compete with the expansion of space itself. But it wouldn't stop there. As the phantom energy grows stronger, it would begin to unravel smaller systems. Solar systems would disband, and planets would be stripped from their orbits. In the final moments, the expansion would become so violent that it would overcome the electromagnetic and nuclear forces, ripping apart planets, then molecules, and finally the atoms themselves. Even the fabric of space-time would be shredded, leaving every single particle isolated in its own private universe, unable to interact with anything else. It is a vision of ultimate solitude, where the connections that bind reality together are untied one by one. A final runaway expansion into the dark. There is a stranger, quieter possibility known as vacuum decay, which suggests our universe might be existing in a fragile state of stability. In quantum physics, systems always seek their lowest energy state, like a ball rolling down a hill until it settles in a valley. We assume the vacuum of our universe, empty space, is at the true bottom of the valley, the lowest possible energy state. But some theories suggest we might be in a false vacuum, essentially a small dip halfway down the hill, while a deeper valley exists further down. If this is true, at any moment, a tiny point in the universe could randomly tunnel through to that lower energy state. This would create a bubble of true vacuum that expands outward at the speed of light. Inside this bubble, the laws of physics would be completely rewritten. The constants of nature would change, and matter, as we know, it might not be able to hold together. Because this wall of change travels at the speed of light, we would never see it coming. It would simply arrive, instantly transforming reality into something else entirely. It sounds unsettling, but it is statistically unlikely to happen for billions of years, if ever. A sudden, silent transformation rewriting the rules of the game. Even if the universe avoids these dramatic endings and simply continues to expand and cool, the matter we are made of may not be eternal due to a process called proton decay. We tend to think of atoms as stable building blocks that last forever. But in the incredibly distant future, time scales so vast that they are hard to comprehend. The protons that make up atomic nuclei might eventually break down. Theoretical physics suggests that protons could have a half-life, meaning they will eventually decay into lighter subatomic particles and radiation. If this hypothesis is correct, then long after the stars have burned out and the galaxies have dissolved, the remaining planets and dead stellar remnants will essentially evaporate. This wouldn't happen quickly. The predicted lifetime of a proton is far longer than the current age of the universe. But given enough time, essentially eternity, even the solid matter of dead stars and rocks would dissolve into a fine mist of particles and light. The universe would effectively become empty of what we call matter, leaving only radiation and black holes in a vast, expanding void. The ultimate dissolution of substance into memory. In the extremely distant future, long after the last star has ceased to shine, the universe will be populated by a type of object that does not yet exist, the black dwarf. Currently, when a sun-like star dies, it sheds its outer layers and leaves behind a hot, dense core called a white dwarf. These white dwarfs are incredibly hot, but they have no internal fusion to generate new heat, so they simply sit in space and cool down. However, space is a very good insulator, and cooling takes a staggering amount of time. It will take trillions of years for a white dwarf to cool enough to stop emitting visible light and become a cold, dark crystal of carbon and oxygen floating in the void, a black dwarf. Because the universe is only 13.8 billion years old, not a single black dwarf exists today. Every white dwarf ever formed is still shining. But in the deep future, these dark, invisible cinders will be the most common stellar objects, drifting unseen through the darkness. They will be the final ghosts of the brilliant stars that once lit up the galaxies, waiting for the end of time. Silent sentinels in the eternal night. Finally, there is a concept that bridges physics and philosophy, known as the Boltzmann brain paradox, arising from the laws of probability in an eternal universe. The idea comes from the physicist Ludwig Boltzmann, who suggested that if the universe lasts forever in a state of random chaos, particles will eventually, purely by chance, bump into each other and form structures. Given an infinite amount of time, it is statistically possible, though incredibly unlikely, that atoms could randomly assemble into a fully formed, conscious brain, complete with false memories of a life it never actually lived. This Boltzmann brain would exist for just a fleeting moment in the void before the atoms dispersed again. The paradox questions why we find ourselves in a vast, orderly universe that evolved over billions of years, rather than existing as a solitary, random fluctuation in the chaos, which is technically simpler for the universe to produce. It serves as a humbling reminder of how special and structured our reality really is, compared to the infinite possibilities of random chance. A fleeting thought manifesting in the deep silence of the void. We've explored the universe through many details tonight. Knowledge builds on itself across centuries. Some things we've discovered recently, others we've known for thousands of years, and some mysteries remain unsolved, waiting quietly for someone to piece them together. And now, as we reach the end of this journey, wherever you are and whatever time it is, I hope these thoughts have given you something gentle to rest with. May your sleep be deep